Large language models estimate intent based on probability. This makes them highly flexible, but unsuited for arithmetic execution, where absolute consistency is required. Applying a standard model directly to a spreadsheet to manipulate cell values introduces the risk of hallucinations and calculation errors. To solve this paradox, Microsoft built Copilot to function as a semantic compiler. Copilot avoids manipulating cell data directly. Instead, it translates unstructured business intent into highly structured deterministic code. This generated block of M code is then handed off to the native Power Query Mashup engine for actual execution. This dual-layer architecture ensures that data transformations remain auditable, optimized, and performant. Deploying AI in a production pipeline requires managing the boundary between the compilation of intent and the execution of logic. Treating Copilot as an autonomous spreadsheet editor leads to compounding errors. Using it as a semantic compiler provides the structure needed for enterprise-scale automation. Consider a standard data ingestion request. A user asks to find and import sales data scattered across a company's files. Copilot executes this request by searching organizational knowledge bases, specifically SharePoint and OneDrive, to isolate the relevant files. However, there is a hard architectural boundary here. Copilot is blind to files saved on local desktop storage. Once a valid cloud-hosted file with autosave enabled is located, the connection creation process begins. Copilot generates the specific M code required to establish a dynamic, refreshable connection, pulling the source data directly into the active grid. But this phase has a strict programmatic limit. During this initial query generation, Copilot is barred from performing complex ETL transformations or column manipulations. Any data cleaning, restructuring, or specific logic application must occur after the initial import is complete. These initial Copilot queries act strictly as extraction pipes. Because they are not transformation engines, post-load processing is a necessity. Once the data is successfully loaded into the grid, the custom column interface takes over as the dedicated natural language compiler. This interface translates plain language business rules and conditions into complex M formulas. Beyond columns, this compilation extends to semantic modeling. Copilot generates data analysis expressions, or DAX, by retrieving metadata during a phase called grounding. In pre-processing, Copilot scans the schema, pulling in tags for data types and synonyms. It actively filters out tables marked as hidden or private. To navigate accurately, engineers must declare table cardinality, defining relationships like one-to-many ratios. Second, they must apply uniform data types and write clear, functional descriptions across the entire model. If these schema standards are ignored, Copilot loses its grounding context. This results in ambiguous join logic. To catch compilation errors, there is a strict post-processing safety check. Before the user ever sees the output, the generated DAX is run through a native syntax parser. This parser validates the mathematical syntax, acting as a firewall to mitigate hallucinations before execution. Copilot's accuracy in generating DAX and M code is merely a reflection of the engineer's underlying semantic model rigor. Despite the flexibility of the compilation layer, it must eventually hand off to the fixed physical constraints of the Power Query Mashup engine. No amount of prompt engineering can bypass the engine's hard programmatic limits. This includes a memory boundary, specifically a 4 GB persistent data cache ceiling. There are also naming and volume boundaries, capping query identifiers at 80 characters and limiting table density to 16,384 columns. But the primary cause of failure for Copilot in active production scenarios isn't memory limits, it is dirty data. Generative models require structured tabular formats to map properties and relationships accurately. They rely entirely on explicit schema continuity. When confronted with merged cells, missing headers, or disconnected unformatted text, this structural continuity fractures. This triggers a cascading failure. The AI suffers from intent recognition failure, defaults to fallback loops, and ultimately generates invalid M code. Deploying a generative compiler on top of unformatted spreadsheets does not fix the data. It only accelerates pipeline failure. There is another programmatic limitation in the Copilot to Power Query workflow. the inability to preserve manual user inputs. When the query refreshes, the engine entirely recreates the output table, deleting any values typed directly into the grid. To solve this, developers must implement a specific architectural pattern, isolating the query output and manual inputs into separate tables. The final step merges them in a subsequent query via shared key columns, ensuring the manual data survives the refresh. Successfully integrating Copilot requires developers to design workflows that respect the engine's deterministic refresh cycles rather than fighting them. When we separate industry hype from the physical reality of the execution engine, Copilot's true role in enterprise data pipelines becomes clear. Professional data preparers retain a strict division of labor. Copilot is reserved for rapid prototyping, formatting, and generating simple measures. The native Power Query editor remains the primary engine for heavy ETL, data cleansing, and complex transformations. This requires a mandate for pre-deployment data hygiene. IT departments must thoroughly audit SharePoint access controls to prevent the accidental exposure of sensitive corporate information during natural language searches. Furthermore, organizations must establish a strict human-in-the-loop validation model for all AI-generated code. Because large language models can confidently hallucinate non-existent functions or misinterpret context, manual technical review is required before promoting any logic to production. In this architecture, generative AI serves as an advisory translation layer. Enterprise data engineering is evolving. AI is becoming the tool used to compile deterministic logic with high speed and consistent accuracy.